In the last video, we took a look at the different types of waves that there are, and I alluded that we can start by just looking at transverse waves and observe that longitudinal waves have the exact same underlying math. And so with that, let's start to think about a transverse wave. This is what you get, say, if you just start shaking a string up and down or something like that. So our prototype wave will look like a cosine function. So something like that. And it turns out that if it doesn't look like a cosine function, if you have some more complicated shape, it turns out that you can obtain any shape you want by a carefully and artfully chosen collection of different cosine functions. So this turns out to be all we need. So let's figure out how to describe it. So this y here is going to be, since we're looking at a transverse wave, how much the chunk of string is displaced from the horizontal position. So the relaxed position of the string would look like this. At this exact moment, it's waving up and down like that. So the value of the y-coordinate is going to depend both on the x-coordinate, where you are in the string. It'll also depend on the time, because we know that the waves will generally move. So we'll take a look at a wave that's propagating to the right and see how that works out. So we can see that the maximum that we can be away, that's the amplitude of the wave. That's going to put an A in front of my cosine. And now I need to start to think about what the rest of the function is going to look like. This bit right here, where we go from one crest to another, like so, this distance here gets called the wavelength of the wave. And that funky Greek letter there is a lowercase Greek lambda. So to draw one, again, going with our favorite third grade paper, you draw it like that. All right. So we need the cosine function to repeat over one wavelength. So ask yourself, as the x-coordinate goes up by lambda, so in this case going from 0 to lambda, what does the argument of the cosine function have to increase by? Go ahead, pause and think about that for a second. Okay, so it needs to go up by 2 pi radians, right? Because the cosine function repeats every 2 pi radians. So we're going to pick up a factor of 2 pi here. And then we'll say x over lambda. So this way, if I put in lambda for x, this will just be 1, and then the cosine will have gone up by 2 pi. Similarly, 2 wavelengths down here, I would have 2 lambda here. So 2 lambda over lambda would give me 2. The cosine would have gone up by 4 pi, and we would have repeated, and so forth. But we also said that we want the wave to move. And what does it mean even to say that the wave is propagating? Well, usually the way you think about it is you look at some crest of a wave and you notice it moving forward. So let's think about what this is going to look like a quarter of a period later. So right now this corresponds to t equals 0. So let's think about it at 1 quarter of a period later. A quarter of a period later, I need this peak to be right here. So that's going to shift everything over by a quarter of a wavelength. Oops. Well, I tried. Something like that. And so now we can see that sure enough, my peak moved over a quarter of a wavelength in a quarter of a period. So we're saying it's moving to the right. And we can go ahead and follow this propagation through. So let's think about, let's say this is a half of a period of oscillation later. We'll figure out what's oscillating in a second here. So now I need the peak to be right there. So it's going to look something like, whoops, like that. And my peak is now half a wavelength down. And then we'll say 3/4 of a period. Again, we'll get into what we mean by a period in a second here. So now I need my peak to be over here. So that's going to look something like that. Whoa. Bad tablet. Let's try that again. There we go. Then finally, at the end of one period, my peak will have moved one wavelength. We'll have to figure out what this period is, but at least we can now say that the period is the time it takes the wave to move over one entire wavelength. So we're just back with what looks like the same wave we had before, but now if we're following the x has moved over to here. So it has traveled in this time, big T, one wavelength. Now, I kept referring to it as a period. And here's what's going on with that. First off, these graphs I've drawn so far are what we usually call snapshot graphs. This is what you get if you take a photo of the string at a particular instant in time. So it shows you at every position what the wave looks like. Now what I'm going to do is I'm going to focus very carefully instead on just this point of the string right there. So just imagine that we had a little bead on the string right there. And now what we can do is we can make what's called a history graph for that bead. So this is a graph of y at x equals 0 as a function of time. So here the x-axis is literally x, the horizontal position. Now the horizontal axis on the graph is going to be the time. So in a snapshot graph, we look at the entire wave at an instant of time, and in a history graph we look at one spot on the wave over all of time. So let's start to map that out. So this is going to be our t over 4, t over 2, 3t over 4, and then big T. So if we go and take a look here, we start out at plus a. So let's go ahead and mark that. So at time 0, the bead was located at the origin was located at plus a. And then we see at time t over 4, it's located at 0. And so then as I continue to think about my bead at the origin at big T over 2, it's located at negative a. Pardon me a second here. It's located at negative a. And then at 3t over 4, it's back at 0. And then finally at big T, it's back up at plus a. Well, look looky there. What have we got? We've got ourselves a different cosine. So what we get is that any particular point on the string is executing simple harmonic motion. Now, depending where you are in the string, the curve will be shifted right or left, but it'll still be simple harmonic motion. So now that gives us a bit of a clue about what to think about here. So we know that in one period, we have to also have the argument of our cosine go through a factor of 2 pi. So I'm going to leave a little space right here. So we're going to have a t over big T here. And now we got to think very carefully about signage. It seems counterintuitive, but if you want the wave to move to the right, you need a minus sign. If you want to move to the left, you need a plus sign. And we can kind of think that through for a second. This is a quarter of a period later, right? I still need it right here at this time 0. T was 0, x was 0. This is all 0. So a quarter of a period later, this has moved forward a quarter of a wavelength. Well, I put in a quarter of a wavelength here, this is a quarter. And I put in a quarter of a period here, this is a quarter. And what I need in order to still spit out a +1 here is for this to add up to 0. So it's a minus sign. And you can do a similar argument to show that if the wave is propagating to the left, you need a plus sign. Honestly, the way I remember this is to just remember that it's backwards of what you think it is. Okay. So this also lets us figure out what the speed of our wave is. Because if we go and look at this, in one period of oscillation, the time it takes this bead to bob up and down, my crest moved one wavelength. So I can observe that the speed of the wave, is equal to the wavelength over the period. But we remember that the frequency is equal to 1 over the period. So the usual way that we write this is we write this as the speed of the wave is equal to the frequency times the wavelength. So the frequency is the frequency at which, if I stuck a bead anywhere on the string, that would be the frequency at which it's undergoing simple harmonic motion. And the speed of the wave will be that frequency times the wavelength of the wave on the string. So okay, let's just try to get practical about this for a second. Let's say you had a 3-meter long wave, and let's say that it had an amplitude of 0.5 meter, and it was moving to the right at 6 meters per second. How would I write this function here to represent that? So let me just go ahead and rewrite it. So our base equation for our prototype wave is y of x and t equals the amplitude cosine of 2 pi x over lambda minus or plus t over t. All right, so what do we need to figure this out? Well, they tell us straight off amplitude of 0.5 meters. This a here is the amplitude, so that would be 0.5 meters when I go ahead and write my version for this. So 0.5 meters cosine 2 pi, and then we still have stuff. All right, what else have they given us? Well, they said 3-meter long wave. So that means the wavelength is 3 meters. Okay, so I can just write x over 3 meters there. What else have they told me? They've told me moving to the right. We remember that if you're moving to the right, that's the minus sign, so we would write a minus sign there. Now, they did throw us for a bit of a curveball here. We need the period. What they gave us was the speed of the wave. But we remember that we can write the speed of a wave as either the frequency times the wavelength, or more useful here would be the wavelength over the period. So we can get that the period is equal to cross multiply around the wavelength over the speed. So we said that the wavelength was 3 meters and the speed was 6 meters per second. So that gives us a period of 1/2 of a second. All right, so then we can go and stick that in for the big T, 0.5 seconds, put in a T, close the parentheses, and that's how we would represent a wave that looked like that. Now, how in general do we know the speed of a wave? Well, if it's a light wave, it's a fundamental property of nature. It travels at just a shade under 3 times 10 to the 8 meters per second. But for other kinds of waves, for mechanical waves, there are various random equations out there. So for instance, here, if we had a string, it can be shown that the speed of a wave on a string is equal to square root of, and I'll carefully write here, T sub s over mu. This T sub s is the tension in the string. And the reason I'm writing it this way is I don't want to confuse it with temperature, which is going to show up in the next equation. This mu is what's called the linear mass density. And so this is the mass of the string over its length, assuming it's uniform. And if it's a sound wave, and I'm not going to justify this in my series of videos on classical mechanics, I do this at the very end. The legitimate derivation for this involves some fairly horrendous math. A lot of books will give hand-wavy arguments that give the right answer, but the arguments themselves are flawed. This sort of thing actually happens in physics more than you might think, where you can kind of intuit the right answer with a quasi-legit argument, and it happens to give you the right answer, or maybe the right answer to within a factor of 2 or something like that. But to actually do it solidly and correctly can be very challenging, and this is one of those situations. For a sound wave, again, if you've seen any kind of hand-wavy argument for it, again, don't put too much stock on it. It's a fairly annoying thermodynamic argument. It's a quantity gamma that depends on whether the gas is monatomic, diatomic, polyatomic, whatever. It's a number that's usually between 1 and 2. Boltzmann's constant times the temperature over the molecular mass, or if you prefer working in molar quantities, be gamma times the ideal gas constant times the temperature over the molar mass. And again, if you've seen a hand-wavy argument for it, don't put too much stock into it. Useful numbers to remember for the speed of sound is that the speed of sound in air at NTP, NTP, remember, is normal temperature and pressure. That's 20 degrees C, typical lab kind of temperatures. That's 343 meters per second. And air at STP is 331 meters per second. So roughly a third of a kilometer per second at temperatures that people actually hang out at. Remember, STP is 0 degrees C. So this is the whole thing. You know, if you see a lightning bolt strike and you start counting the seconds until you hear the thunderclap, the light gets to you lickety split because it's traveling at 3 times 10 to the 8 meters per second. So there's, you know, it does not take very long at all for the light to get from a lightning bolt to your eye, but it's going to take some time for the sound to make it there. And so if you start counting off the seconds from the lightning bolt to when you hear the thunderclap, every 3 seconds means an extra kilometer away that the lightning bolt struck. Or if you insist on working in miles, it's count 5 seconds to get for every mile the lightning strike was away. Now, it is possible to have the speed of a wave change, and this can be done by changing the medium. Notice here in both cases, and this is the one thing that just generally shows up to be a case, even though derivations for wave speeds are generally different for just about everything, there's always some inertial property, some mass-like thing in the denominator inside a square root. That's a common feature. But anyway, let's say that you have a string like so, and then you tie the string onto a rope like that. So here the linear mass density would be small, and here the linear mass density would be large. I'm sorry, not lambda, mu. And since the wave speed goes inversely as the square root of the inertial property, if we have a small linear mass density, that's going to mean that the wave speed here is larger, and here it's smaller. Okay. So here's the question for you to think about, and I do want you to seriously pause and ponder this before we go on. Let's imagine I have a wave going down the string here. Now the way I drew this, I made it look like the wavelength is the same. This might or might not be the case. So I want you to think here where the speed of the wave drops, going from the thinner string to the fatter string, will just the wavelength change? Will just the frequency of the wave change? Will they both change, or will neither of them change? So pause and think about that for a bit, and then we'll get back together. Okay, so believe it or not, in this situation here, only the wavelength changes. The frequency will stay the same. The only way I can think to justify that at all is to tell a story about a very well-organized jailbreak. This is a story that was told to me when I was first learning this. Maybe it'll be useful for you. So what we imagine is at some prison, the prisoners discover a flaw in the security system, and that they notice that the surveillance cameras won't notice them escaping over the wall about once a minute. So once a minute they notice that none of the surveillance cameras are looking at their escape spot. They figure that out, and so they orchestrate a jailbreak where the prisoners escape over the wall once per minute. So the prisoner goes over the wall, ends up over here. So now let's say initially the prisoners are running down some road. How far will this prisoner be able to run going down the road in front of the prison in a minute? I'd say a pretty good distance, right? And another minute later, they're over here. And so at this point here, when the prisoner arrived here, that's when we picked up another prisoner there. All right, so now let's say here, though, they run off the road, and now they are running through a field. Well, they're not going to be able to run as fast down a field, right? So where's this prisoner going to be a minute later? I don't know, maybe here. And then again, maybe they're a minute after that. And then let's say after that, their path takes them through a swamp. Well, they're certainly not going to run as fast in a swamp as in a field. So probably not covering very much distance at all in a minute. And like I said, this was a very well organized jailbreak. So over here's the SWAT team picking them back up. What is the rate at which they're capturing prisoners? 1 a minute. So the frequency of the prisoners never changed. Anywhere along this whole path where you sit and you look, once every minute a prisoner is going to go by you. However, the wavelength of the prisoners changed. The slower the speed of the prisoner, the slower the wavelength. The slower the separation between, the less the separation between our prisoners. So remember, if the speed of a wave changes, the frequency remains the same. Only the wavelength will change. Alrighty. So in the next video, we'll go ahead and start taking a look at sound waves. Catch you there.